mass, which is nice unison there, times acceleration. The math problem is 6 is equal to 3a. That's the math problem. So a, 6 divided by 3. So the fancy math, 2. So that's 6 newtons divided by 3 kilograms. What are the units of the 2? There are 2 answers. What are the units? Well, look at this. What did I divide?
Newtons and kilograms.
Okay, so is 1 over something, or are they multiplied, or what do you do with them? Yeah, we divide it, because that's, that fraction there is a division. So newtons, 2 newtons per kilogram. That is a perfectly legitimate answer. But what were the units of acceleration that we just did in chapter 3?
Meters per second. Meters per second. Squared.
There we go. Meters per second squared. So another legitimate answer is 2 meters per second squared. So how do we get from newtons per kilogram to meters per second squared? Well, a newton is what's called a derived unit. The 3 lines of equal signs there mean it is true by definition. A newton is a kilogram times a meter per second squared. Or I could write it as kilogram meter per second squared. I do want to point out that I feel like I've mentioned it before, but possibly repetition here. When I have 2 units multiplied together, putting a dot between them is very useful. It's a kilogram times meters over second squared. That's by definition. So if I divided by kilograms, that would go away and 1 would show up under here. So a newton per kilogram is a meter per second squared, by definition. It's just set up that way. So over here, either answer is correct. Questions? All right. Let's stick with our 3 kilogram box. I have 6 newtons and I have 5 newtons. What is the acceleration now? I do realize there was one mistake over there. Let me address that. I'm asking for a vector acceleration. I need to somehow indicate direction. I've given no indication really about what direction 2 meters per second squared is in. So I'm just going to add positive directions to the right. Now I'm good. All right, over here. I'm going to do the same thing. I'm just going to say to the right is positive. If that bothers you, because where the unit vectors, you can make it positive I hat if you want. All right, so we're going to plug in F equals ma. Total force. The mass. Times acceleration. It's positive 11 newtons because they're both in the positive direction. So my acceleration, 11 thirds units. I think somebody said it, but I'm not 100% sure.
Newtons per kilogram.
Yeah, that works. or 3.67 newtons per kilogram, or 3.67 meters per second squared. In 151 and 251, I might throw an extra wrench into it by saying 3,000 grams instead of 3 kilograms. But I tend not to do that for 110. All right, let's add slight complication to it. All right, so still gonna say to the right is positive. I got my 3 kilogram box here. I got 6 newtons that way, and I've got 5 newtons that way. What is the acceleration of the object now? Or how would you find it? Is, oh, you,
I would, add the 6 newtons plus -5 newtons.
yep, absolutely. The net force, we're plugging in F equals MA again. The net force is 1 Newton in the positive direction is equal to 3 kilograms times the acceleration. So the acceleration, 1/3 or 0.33 repeating. Newtons per kilogram or meters per second squared. Questions to hear? I'm about to make it look more complicated. All right, we'll go back to our 3 kilogram box here. I got 6 newtons pushing on that way, I got 5 newtons pushing on it that way. What is the acceleration now? Or perhaps the hard part, what is the total force acting on it now? Yeah. That's a common mistake.
10 meter per second square? No.
No, looking for total force right now. Well, if you're going for total acceleration, no, it won't be that. But the more intermediate question is what's the total force?
Is it 1 again? Is it 1 again?
No, not 1.
Is it 11?
It is not 11.
Do you multiply them?
Nope. How?
You do the 6 newtons and then the I
Keep going.
plus the 5 newtons with the I.
They're not both I.
No? I mean a J. It's a
J, yeah. All right. When it's a two-dimensional problem, we cannot get away with just plus minus. We have to bring in the hats. So I'm gonna define I hat to be this way, and J hat to be that way. They're perpendicular to each other. And so the total force is equal to mass times acceleration. And so it's 6 newtons I hat. I think you just said I and J, the hat indicates that we're talking unit vector. 6 newtons I hat plus 5 newtons J hat equals 3 kilograms times the acceleration. It's a little bit trickier in some sense than what we were dealing with. If I wanted to combine the 5 and 6, I can do a little Pythagorean theorem, but let's not do that yet. How do I solve for acceleration now?
5 by 3.
Yeah. Divide this side by 3 kilograms. Divide this side by 3 kilograms. They cancel out here. I'm left with just acceleration all by its lonesome self. Now over here, I have 2 things I'm dividing by 3 kilograms. So this will be 6 thirds I hat plus 5 thirds J hat. Newtons per kilogram. And if you want to put the units right next to the numbers, that's fine. Or my acceleration, 2 meters per second squared I hat plus 1.67 meters per second squared J hat.
Which one's the answer?
This is legitimate, they're both legitimate answers. I just put this in decimal form and that fraction form. And I could put the units right next to the numbers or put this in parentheses and put the units there. Whether you do newtons per kilogram or meters per second squared, depends on your mood. All right, let's make it sound more complicated now. I want the magnitude of the acceleration. The magnitude of the acceleration. Well, to find magnitude, I need that. I got 2 vectors here. I go 2 in that direction, and then I go 1.67 in that direction. Just like we had just done. I go 2 in this direction, and then I go 1.67 in this direction. And my resultant, the magnitude, well, the resultant is a vector from the start to the end. And the magnitude is just however long that is. I have a right triangle. We make those perpendicular to each other, all for make this part easier. So if that's my resultant, how would we find the length of the resultant?
Would you add the 2 and the 1 and subtract?
No. I was about to say something simpler, but that's not what you're, it's simpler, it's just more correct. Say it again?
Is this the one with the a squared, b squared?
Yeah, give me the whole formula.
A squared plus b squared equals c squared?
Yep. So 2 squared plus 1.67 squared is equal to r squared. Whatever that is, so that is 4 plus 25 ninths is equal to r squared. 61 ninths is equal to r squared. R is the square root of 61 ninths meters per second squared. If you have a calculator, it'll probably be easier. That's what so that the 25 ninths is good with 76 and 25, yeah, 61. All right, by the way, F equals ma, this has a name to it. This is Newton's second law of motion, or generally just shortened to Newton's second law, or when I'm writing it, I will just often abbreviate it as N2L. It's Newton's second law. The whole idea that object wants to stay at the constant velocity, that's Newton's first law of motion. So when objects do change their velocity, we have Newton's second law. And then there's a third law that we'll get to. Not yet. All right, let's spend a little bit of time talking about friction. So if I take an object and I slide it on the table, it stops. Once I let go of it, it started slowing down. Because it was slowing down, because the velocity changed, there was acceleration. Because there was acceleration, there had to be a net force acting on it. Well, if we did a force diagram of it while it was coming to a stop, we have weight acting down, we have normal force acting up, and we have friction acting that way. So the first question is, what affects the actual friction? Opening it up for speculation about what affects the friction that was acting on the box. It's okay if you're wrong. I'll wait for someone to speak. Oh. What do you think affects the friction?
The force you put on the box.
That I put on it? Is that what you're talking about? Except the friction was acting on it after I stopped touching it.
The table,
What about the table?
the surface of the table.
You're half right. There are two objects involved.
The surface of the table on the bottom of the box.
Yep, there we go. There's one thing. So friction depends on the touching surfaces. So there's a table that we'll eventually get to that where you have to look it up, the two materials that are working again with each other in order to be able to solve the problem. Okay, what else?
Is it the weight of the box?
All right, so if I push on the box, it went that far. I try to push with the same amount of force each time and see how, roughly the same. Okay. All right, so weight of box. more weight to the box. Or did I? It seemed like it stopped earlier. But did I actually change the weight of the box?
You added weight into it.
So what did I change? If I didn't change the weight of the box, something changed.
Total force. Total force?
Not, just putting them in there does not change the total force. Once it starts moving, yeah, the friction's different, the total force would be different. But more specifically, think about the force diagram involved and the forces acting on the box.
The mass.
Sorry?
You changed the mass.
I did change the mass of the box, but not a force.
The normal force?
Yes. What I really changed is how much force the table is required to hold up. So friction really depends upon the touching surfaces and the normal force. This was figured out in the late 1700s, and it really hasn't changed since. Not much. There is a group at NC State who's trying to see if they can figure out a more thorough explanation for it. But the trouble is, engineers, very practical people, they have something that works. Why bother going in more detail? Physicists often, most physicists don't even deal with friction. That's more of an engineering thing. So it's left in this, yeah, good enough from late 1700s. All right, so we need to somehow combine these two into a formula because everyone knows a formula. So I want to break this down into two